Welcome to the Newton tutorial series. I'm Mike Cruz with AC-Tek, and in this tutorial I'm going to be showing you how to automatically create a particle set, and I'm going to be explaining what these graphs in the particle library are used for. So if we go to the group list tab, we've already talked about the inputs on this page and how to tweak your particle set. But you can also use Newton to automatically generate a particle set for you. And then you could, for example, use that particle set directly in a simulation. Or you could take that auto-generated set and you could make tweaks and small modifications to it or large modifications to it and turn it into whatever particle set you want. So this grid on the left-hand side, we haven't talked about this yet. And what this grid is it contains the parameters that Newton will use when it automatically generates a particle set. So the only two parameters, these two parameters at the bottom, don't apply to that. These are separate. But the rest of these 7 parameters are used for creating that particle set. Down here at the bottom, we have the solids ratio, and that is what Newton uses to determine how much material to generate when you're generating particles using this particle set. That solids ratio is very important, and it needs to be calibrated for each of your particle sets, including any that you might automatically generate. The particle sets that are built into Newton, we have already calculated this solids ratio for those particle sets. But any particle sets that you create will need to be calibrated. And one of the following tutorials will explain in greater detail what the solids ratio is and how you calibrate it. And the plot spacing is purely the distance between these particles down here in the rendering window. So if I turn this down to 20, or 15, it's just moving those particles further apart. So if I had some huge clusters, I can space them out better so that I can actually see all the particles in the set. So that has nothing to do with the actual particle set. But the rest of these 7 parameters are used when we auto-generate a set. So basically, to auto-generate a set, you click this regenerate button here. And what that does is it's going to throw away the current particle set. It's going to throw away all those clusters and create a new set. So generally, you don't want to do this on one of the built-in particle sets. You don't want to replace a built-in particle set with your own. You want to just add a new particle set. So rather than just clicking the regenerate, first you want to create a new set. We'll call it auto set. And now I can regenerate that set, and we'll create a particle set. So something else to note about this input grid is that when I'm looking at any of these particle sets that are built into Newton, this input grid, it doesn't apply to any of these particle sets because these particle sets were all created by hand. They were manually created. We didn't use this auto-generate feature. So all of these parameters have nothing to do with the particle set. These are just the parameters that would apply if I wanted to overwrite this particle set. I could change those parameters. But the only parameters that do actually apply, the solids ratio, is attached to this particle set, and the plot spacing again is just for viewing the particles in this window. But all the rest of these parameters have no meaning because we didn't generate this particle set automatically. But now when I go to my auto set, when I click that regenerate button, it's creating this particle set based on those parameters. And so if I go and tweak these parameters and I say 20 and 150 and 40, well, the parameters, they don't mean anything to this particle set unless I go and regenerate it again. So the point is, these are purely input parameters that will be applied once I hit that regenerate button. So let's change this back to, what was it, 100, something like that. So now let's go to our size distribution curves, and actually let's stay on here for a moment. So when I generate this, the number of groups is the number of clusters I create. The maximum size is my cluster top size, the minimum size is my cluster bottom size, and the average size is the average cluster size for the set. The uniformity and the size distribution factor apply in creating the particle set, but they apply more to this curve here that I'll talk about in a moment. The size ratio specifies what's the maximum sphere size ratio that I want to allow for this particle set when I generate it. So basically this is saying the max that could be is 1.25, and for this one that I just generated, it happens to be 1.23. So if I took my biggest one, 24.6, my biggest radius, and divide it by my smallest of 20, I would get that 1.23. Alright, so let's go over to our size distribution curves. We have 2 graphs in this window. The top graph is a percent passing curve, and the bottom graph contains your particle counts and particle weight percent by weight again in bar graph form. So going back to this top curve, we've got a percent passing curve, and each of these stars represents one of the clusters that we generated. On the x-axis, we have our particle size in millimeters. So, obviously our smallest here was 40, and our largest was 100. And on the y-axis, we've got that percent passing. That red line is the Rossen-Ramler curve, and that's the curve that Newton tries to base these auto-generated sets on. So what it will try to do is, as you modify this shape of this curve, Newton will do its best to create the particles so that they fall in line with that curve. But you're not necessarily always going to be able to make the particles follow the curve exactly. So then down on the bottom, again, what we have is there are three separate bars that we can apply to this bar graph. We can do the percent by weight, which is showing me for each of these clusters going from 40 up to 100, what's the percent by weight, the very same information that's in this column. We have the particle count, and this is saying what percent of the particles, according to sphere count, belong to each cluster. So, for instance, for this smallest cluster, this generated group, this single sphere, 9% of the spheres in the entire particle set belong to this cluster, and 4% of the spheres that would be generated would belong to this next one, and so on. And then, of course, the cluster count is the same thing, except rather than talking about spheres, we're talking about the entire cluster. So these percentages will fall directly in line with my cluster count per 10,000. So you'll notice this 2648 divided by 10,000 is about 0.26. So if I look here, we've got 26%, and my, say, this 93 one right here, 93, which one is that? That's this one right here. 300 divided by 10,000 is approximately 0.03, which is 3%. That's right there. So all that's showing, again, is my cluster count per 10,000 in graphical form. But generally, you're going to want to just look at your percent by weight and your particle count. And what this is showing is how is my weight distributed in this particle set? Do I have a lot of particles in the middle? Do I have a lot of particles at the top, or a lot of the weight at the bottom? How is that distributed? So now let's talk about modifying this curve. Let's talk about these two parameters here again. Let's increase the number of groups to 20 so we get better resolution, and let's just regenerate that. Okay, so the uniformity, what that does is it changes the shape of this curve. The uniformity controls how strongly is this an S curve. So, for example, if I turn that down to 1 and hit regenerate, we've got basically a straight line. There's no S shape in here anymore. And similarly, if I go all the way up to, say, 10 and regenerate, well, now we have a super strong S curve. The S is so strong that these first couple of particles, there's basically none of them there according to our percent by weight. And same at the top. These last couple, we've got almost no clusters on those bottom ones and the top ones. Our percent by weight is tiny because the curve is just too strongly shaped. So you want to keep this uniformity usually around 2 to 6 or so. So if and the other thing you can note is when you turn this uniformity up, clearly we're distributing the particles more in the center, which is exactly what this curve shows. We've got very little on the outer regions, and most of the weight is in the center. If I turn that down to 6 and regenerate, see, now we're starting to spread it out a little bit more. If I go down to 3, well, now we're spreading it out even more with a few concentrated down here at the bottom. Alright, so then the size distribution factor, what that says is how do we distribute these clusters along the curve? Do I distribute them evenly spaced, or do I concentrate them towards the low end or concentrate them towards the high end? So if I turn this size distribution factor down from 1 to, well, first of all, a value of 1 means we're going to evenly space those clusters between 40 and 100. And if I turn it down to 0.5 and hit regenerate, it's going to concentrate the clusters up toward the upper end of the curve. So now you can see if we look at our sizes, we've got a lot that are sized in 80 to 100, and fewer are sized 40 to 80. Because right here, these top half of the clusters, this represents a difference in size of 20 millimeters. But going from 40 to 80, that represents a difference in size of 40, and we've still got the same number of clusters there. So we're just concentrating them up. Likewise, if I take my size distribution and turn it up to 2.5, now we've got them all concentrated towards the bottom rather than the top. But certainly above a value of, what, 4 or 5 or something like that, you get to a point where almost all your clusters are at the bottom. So generally that uniformity, we want to keep it between maybe 0.25 and 3, something like that. And a value, there's nothing wrong with a value of 1 either, just keeping them evenly spaced. It's very reasonable. Oops, oh, sorry, I didn't mean the uniformity. I meant the size distribution. We want to keep this, between 0.25 and 3. And like I said, there's nothing wrong with a value of 1, and that simply means that we're going to be spacing these clusters equally along the length. So, what do we actually see when we generate these particles? Alright, let's change our plot spacing to, say, 15, maybe even 18. Alright. So I want to actually change one more thing here. What do I want to do? I'm going to increase my max size to 120 and increase this to 60 and regenerate. That'll be good. Okay, so what we've got here now is we've got 20 clusters going from 40 to 120. And these are my shape parameters for that curve. And there's my size ratio, that 1.25. Now if I go back to my group list, let's take a peek here. How did Newton create this particle set? Well, what it does is it's going to start with this bottom particle and says, well, the smallest particle makes sense to just create a sphere out of that. The smallest particle is going to be the smallest one. The simplest cluster type would be a sphere. So if I create a sphere that's sized 40, its radius is going to be 20. Simple. Then it looks at the next one and says, well, according to this distribution factor, where does that next cluster have to be? And because these are evenly spaced, it says, well, the next cluster has to be exactly 44.2 millimeters. Okay? So what kind of cluster should that be? Should that be a sphere as well? Well, let's see. If I was to make this a sphere, what would my radius be? My radius would be 22.1. So my ratio of 22.1 to 20, does that obey this size ratio of 1.25? So if we break out a calculator here, 1 second, if I say 22.1 over 20, 1.1. So it's acceptable to make this a sphere because my sphere size ratio stays within what I've designated, my 1.25. How about the next one? Well, the next one is also a sphere, because that cluster size gives me a sphere radius of 24.2. And obviously 24.2 over 20 is still less than 1.25. And then we get to the next cluster and we say, okay, this cluster needs to be 52.6. So what would that radius be? That would be 52.6 over 2. That would be a radius of 26.3. Well, if I divide that by my smallest radius again, well, now we've exceeded that size ratio, so we can't do that. We can no longer use a sphere and still maintain the size ratio. So what Newton does, it looks in its cluster library for these auto clusters and says, well, what's the next largest one that I have? The next largest one is this little 4 cluster. It's this tetracluster that all of these ones here, they're all using that same tetracluster. All we're doing is changing the overlap of the spheres. So it says, well, let's make a tetracluster, and let's push the spheres together small enough that it matches the cluster size that I'm looking for. Alright, so we've got 4 spheres in there, but they overlap so much that the total size of the cluster is only 52.6. And then Newton says, well, what should the radius for these spheres be? Because I could certainly use smaller spheres, and I could have less overlap there. But it says, nope. Well, when we move up to the next cluster, let's maintain that minimum radius so that it matches the very first one. It says, okay, well, let's create it with 20 millimeter radii, and let's smash them together so that we can match this cluster size. Alright, and then it goes up to the next one and says, okay, the next one has to be 56.8. Can I still use a 4 cluster and space out the spheres so that my sphere radius matches? And it says, yes, I can do that. We just stretch them out a little bit further apart, and now we have a larger cluster. And so on. We go to the next one, we go to the next one, the next one, the next one. And then it got to this one, and you notice that my sphere radius is a little bit bigger. So what happened here is we're comparing this cluster to the next one. So what Newton did after it finished this cluster, it said, well, if I create this cluster and I want to keep my sphere radius at 20, can I stretch out these spheres enough to make this size equal to 77.9? Can I pull the spheres apart far enough? And it said, no, there's a problem, because if I keep the sphere radius at 20, then when I try and stretch those spheres out, I'm going to have gaps between the spheres. The cluster will no longer have all the spheres physically touching each other. There will be no more overlap. And it doesn't make sense to create a cluster where you have spheres that are physically not touching each other. That doesn't make sense. So Newton says, nope, I can't keep this radius that small. I need to increase the radius a little bit so that there will still be some overlap. In between those spheres in the cluster. And then it created it. And now you can see that these next couple of tetra clusters, they're still tetra, but we're increasing that sphere radius because we've reached the limit of how far we can stretch out the spheres. So we simply keep increasing that radius until all of a sudden, well, once we get above 25, certainly 25 divided by 20, that's our limit for the size ratio. So once I finish this cluster right here, certainly the next one up is going to have to change shape again, because I can no longer maintain both the spacing of the spheres and the sphere radius. So the next cluster it grabs is this 6 cluster. So we've got 4 clusters and then one on the top and one on the bottom. So again, it starts over and it says, well, let's start out with a specific overlap, and let's start out with our as small a radius as we can get for this size. And for this particular cluster, clearly it didn't start out exactly at 20 because this was a little bit larger than that. So it started out with 21.8, and the next one it increased that radius a little bit more, increased the radius a little bit more, and a little bit more. And again, now we're reaching that limit of 25. So these last 2 clusters, it said, well, we have to change shape again. So what's the next cluster we could use? And it happens to be this 8 cluster. So it says, all right, well, let's start over with the 8 cluster. Let's determine our overlap and our radius so that we can use this 8 cluster. And that's how it does. It'll start out with the smallest cluster and work its way up toward the top. And it'll try to obey keeping those sphere radii within that limit you set. And it'll space out the sizes according to your distribution factor. And then obviously the uniformity in the average size, this is going to be, how do we determine the percent by weight? Because those percent by weights are determined by, reshaping the curve. So that's how we auto-generate the set. And if you compare it to, let's say we compare it to our 60 to 180 set, there's a lot more variability in this 60 to 180 set. And that's because, like I said, we generated this one by hand. We didn't use the auto generator. And that is a small limitation of the auto generator. Currently, it can only use, 1, 2, 3, 4, I think there's 5 or 6 different shapes it will use when it auto generates a set. But we are working to include, some of the rest of these shapes in there, because we want to make that auto generator much better so you can get a good variability in the size and shape of the particles that you can create. But for the time being, you're limited to just these. And for the time being, that's why it's better to take one of these particle sets that we made and instead just go ahead and copy this particle set and change it as you see fit. Because now let's look at the size distribution curves. Here's our 60 to 180 that's built in. And what if I go to my auto set, and what if I make this a 60 to 180 with an average size of, say 90. Let's regenerate. We want a little bit more of a uniformity, a little bit more of a shape factor there. So let's regenerate it again. Okay. So now let's turn down my plot spacing. 12. So it's a similar particle set to what we saw before. If we compare that to the built-in 60 to 180, Well, yeah, that's following a very similar type of curve. So we manually created the 60 to 180 set, but we still did our best to follow that same kind of Ross and Ramler curve. Now, if we want, probably one of the best ways to create a particle set is to do something like this. Say, well, let's start out with what am I looking for in a particle set? What do I want my minimum and my maximum size to be? And how do I want to distribute my percent passing? So let's say I wanted a set that's just like this. Well, how many clusters do I want? Well, maybe I don't want 20. Maybe I want 40 clusters in here. So let's go ahead and create this entire particle set. We've got a really good distribution. If we look in our window, it seems like the clusters are distributed relatively okay. So now what do? We go back to our list here and we say, okay, how do I want to tweak this particle set? I've got 40 clusters I can play with. And it auto-generated these shapes for me, but you know what? Maybe I don't want that 8 cluster. Maybe I want to use something like a 18. Maybe I want to change that top cluster, so instead of being that one, it's going to be this one instead. Well, I can just manually go ahead and change that group type because Newton automatically generated all these groups. But after you create that particle set, you are completely free to change any of the sizes, any of the percents, the cluster count, or any of the group types and customize it to be your own cluster, your own particle set rather. So when I made this an 18 triangle, what's my sphere radius? Well, the smallest here is 30, the largest is up to 36. So, and we're right smack dab in the middle. So this is a reasonable cluster to use for this size. Well, how about the next one? Maybe I still feel like, do I really need 3 of these same clusters that are almost the same size? Maybe I want to change that as well. Let's go down and say, well, how about a 12? Overlap 50%. What do we see there? Those spheres are looking a little big. How big are they? 41.8? Well, that means now our sphere size ratio has jumped. Because remember, our limit was 1.25. But as soon as I put this one in here, it said, well, to scale up this cluster, that sphere radius needs to jump up to 41.8. So we're no longer obeying this size ratio of 1.25, but maybe that's okay. Maybe we just wanted to start out with the size ratio, and now as we tweak it, we know the size ratio is going to fluctuate. It might be a little bit higher. But it's still smaller than that maximum recommendation of being less than 2. So we're okay with that. And maybe we're going to go down here toward the bottom of the particle set. And maybe we're going to say, well, I don't need 20 different tetraclusters, or 20 of the same tetraclusters that are just scaled. Maybe I want to change this into a 2. So let's do a 2 overlap right there. And what do we see? Ooh, our sphere radius is actually pretty small, isn't it? 23. Now we're jumping up to 1.79. Is it necessary to do this? Yeah, maybe I don't want to use that one. Let's delete that cluster. And maybe I want to, instead, let's put that 2 overlap up here somewhere. Because these clusters are a little bit bigger. So if I say 2 overlap 10%, we're still a little bit small, aren't we? Still 24, still increasing that. Alright. Let's go up to here. Let's do it with this one. Make this a 2 overlap 10%. There we go. Now you can see the radius of those spheres is pretty similar to the rest of them. It's right in that same neighborhood. And you know what? Maybe I want to make a few of these. Maybe I want to make this one up here a 3 flat. Because I like the shape of that 3 flat. Where is it? Right there. There's a 3 flat. And again, our sphere radius is matching, and it all looks all right. So you can go through here, and like I've mentioned, you can change any of the group types. You could even change the sizes. If I wanted to make this, say 100 and 125, and I can do whatever I want to this particle set. It's just easier to use a built-in to use an auto-generated set just to start yourself off. And then you can see as I make these changes, I'm changing the curve. See what I did there was I had increased that size to 125. So obviously 125 is over here. So I kind of slid this particle out of position. But now if I take this 125 and I just move it up and move it up again, now it's right in between where it should be. Now if I look at this, it should update that. And I think it did. It's just tough to tell from the graph because we still have we're still going to have a cluster sticking out. It's just where is that cluster positioned in our list. So the point is that this curve is just a starting point for your particle set. And the ones that we've used that built into it, they follow a similar curve. You know, some of them look more of an S shape than others, but you know, the 30 to 60 and the 25 to 50, they have fewer particles, so it's tougher to follow that curve exactly. So I think this pretty much covers how to create these auto particle sets, or how to auto-generate a particle set. Actually, there is one other thing I wanted to talk about. So going back in here, we talked about our uniformity, we talked about our size distribution factor, we talked about how those will shape that curve. And the size ratio, we know what the size ratio is, and we know how it uses that size ratio, but we have to be careful with the size ratio as well, because what if I want to generate a 60 to 180 particle set, and I turn up this size ratio and call it 4, and I hit regenerate? Well, what did it do? It just created a particle set of all spheres. And we've talked in the previous few tutorials about how spheres are really rolly, and they don't look like realistic particles. They don't flow like realistic particles. And it'd be a bad idea to have a particle set with only spheres. But why did it do this? And it did this, you know, just like we were talking about. It started at the bottom and said, well, my smallest one is going to be a sphere with radius 30. And it went all the way up to it got all the way up to the top. And by the time it got to the top, a 180 millimeter cluster would have a radius of 90. 90 divided by 30, well, that's only 3. And obviously, a ratio of 3 is still less than the limit we set at 4. So you can use this size ratio to force Newton to use, you know, some of the similar clusters or some different clusters. So if I instead made this 2 and hit regenerate, see, now we only see a bunch of spheres and a bunch of our tetra clusters, because in order to match that radius, it didn't have to switch shapes as much. So what if I say my size ratio is, let's bring it all the way down to 1. So now we see the full range of clusters, all from a sphere to the tetra to the 6 and the 8, and then the top size is this this 27 cluster. It's 3 by 3 by 3. So by changing that size ratio, we can force it to use that full range of clusters. And again, we're going to change the auto generator so it's using more shapes, more complex shapes, and more variability. But for the time being, this is what you can use. So I think that is all I wanted to cover for this tutorial. And if you have any other questions regarding your particle creation, please feel free to send us an email at info@actek.com. Thank you.